So I start a lot of the slideshows with a quick little objective thing, seeing what you should know either at the beginning of the slideshow or at the end of the slideshow. And this one has a lot of stuff because we're going to cover a lot of stuff. We're not going to cover all this stuff today. So we'll talk about function notation. I'm assuming that last year in pre-calc you made the transition from y equals to f of x. Is that a safe assumption?
Yeah. Yes.
Beautiful. Good. Evaluating functions might be a little tricky. I've got an example for you. Talk about domain and range. Easy peasy. We've talked about sketching graphs of functions already, basing them off the mother function, taking a mother function, figuring out what do I need to do to that mother function to get the function that we're looking for. And again, I have an example of that today. We'll talk about composite functions later. What's a composite function? No? Then it's a good thing we're talking about it. Solve some polynomial inequalities, piecewise functions, and last but not least, we'll review the step function, also known as the greatest integer function. Do you remember that one? That's a little dash, you know, that kind of thing. But again, we'll get up to maybe here today. I don't know, somewhere. We'll just go until we run out of juice. Okay, a lot of stuff going on in this picture. Domain and range. You should know that domain is all the possible x values, range is all possible y values. I would be surprised if you didn't know that. However, the reason I included this is because this sometimes causes problems for people. Independent versus dependent variable. Okay, the independent variable is the x. Why is the x the independent variable? Because you choose what you want x to be. If we look at a function like y equals 2x plus 3, and you start plugging in numbers, almost exclusively you'll pick a number for x and put it in. So let's say we put in 2. Okay, it's going to spit out an answer. I forget what the function was. 2x plus 3, is that what I said?
Yeah.
All right, we'll go with it. Put in 2, you get 7. The reason y is called the dependent variable is because the value of y is dependent on the value that you choose for x. Okay. The rest of this you already know, and you probably knew that already, but I find a lot of people forget which is which. Now the fun begins. Okay, so we have a nice little function up here on top, x squared plus 7. And we want to start, we'll start with something fairly easy, and then we'll ramp up until we get to this monster in C. So what does that mean? Victoria?
So for every x in the equation, you substitute in 3a and then solve it.
Perfect. Any problems with that? Okay. Before we get started, for instance, what would f of smiley face be? How would you handle that? Substitute smiley face wherever there's an x. It doesn't matter what it is you're talking about. You just take that thing and plug it into the function for x. All right, Victoria, back to you. So what would this be? F of 3a would be equal to?
3a squared plus 7.
3a quantity squared plus 7. That's the first step. Okay, plug it in. Second step, evaluate. What's 3a quantity squared? 9a squared plus 7, all done. Any problems there? Easy? Good. Part B. What's f of b minus 1? Again, we'll plug and chug first, and then we'll evaluate. Noah.
Yes. It'd be b minus 1 and then squared that plus 7.
Do you know how to multiply that out quickly?
Yes.
Are you doing, how many of you are still doing b minus 1 times b minus 1 and then foiling it? Okay, so you know the shortcut, right? What is it? Square the first term. Good. Multiply the two terms, multiply by 2, so minus 2b. Or not 2b, that is the question. Beautiful. How are we doing so far? Okay, now this is where the wheels fall off the bus. Can I erase this? Hi.
Hello.
What'd you bring me? Present?
Mr.
Oh.
Poison.
Just some hats.
Yeah.
Not that exciting. Are we making something?
Yeah, a t-shirt.
Just a t-shirt?
Well, kinda, in a way. I like designing a t-shirt and we're gonna make it.
Oh, okay, gotcha. Pattern to put on a t-shirt.
Right.
Not the t-shirt itself. Pretty much hasn't changed in a long time. Okay, beautiful. Let's get rid of this. Let's get rid of this. There we go. And let's do part C. This is really important. It's the foundation for probably 2 or 3 months of work we're going to do in here. Have you seen that before?
Yes.
Beautiful. Have you worked with it before?
Yes.
Beautiful. So maybe this will be easier than I thought it would be. What's f of x plus delta x?
Is it x plus delta?
Colin, right? Yeah, go.
Is it x plus delta x squared plus 7?
X plus delta x squared plus 7. Well done. We'll come back and simplify it in a second. What's f of x?
X squared plus 7.
Good. Trick question. Important point here though, minus, you want some parentheses in there. Single most common mistake in the entire course is forgetting that set of parentheses. X squared plus 7 all over delta x. That's not an f of delta x, that's just a delta x, so it just stays as delta x. That's the first half of the problem. Okay? Being able to substitute in x plus delta x where it needs to go. Second part is evaluating. Okay, what's that squared? Using the same method we just talked about.
X squared plus 2 delta x. And then plus
Wait. Go back to this one.
2
What
delta
is?
x.
Nope.
Oh, 2 x.
Good. 2x
Delta x.
delta x.
And then plus delta x squared.
Good. Plus 7. Don't forget that guy. Minus x squared minus 7. All of that mess over delta x. Well, that makes me happy because that goes away, that goes away, that goes away, and that goes, whoops, and that goes away. 2x delta x plus delta x squared all over delta x. Now what? Go. Tell me your name first.
Steven,
David.
can you take out delta x over delta x and then you could make it, so it'd be 2x plus delta x is the final answer.
Yes, but talk me through that again. How'd
So
you do that?
I just kind of like use, like you cross off the bottom, but you have to take it out of each one at the top.
Yeah, let's. Yeah, but let's be careful with our math.
Yeah.
So I'm going to actually factor out a
Take
delta
out
x.
delta
Yeah.
x, yeah.
Whoopsh, whoopsh, and there's our final answer. Okay, good. We get the same plot. I just want to make sure that everybody's using good math there. Why is that little bugger there? Nick?
Because if it was 0, then like it would be, what's the word? Like it can't be 0 because the delta x is on the denominator.
So no zeros in the denominator. Okay, so we just slap that in there and then we're good to go.
Yeah.
Yeah, good, good. Question, comment? Question, comment?
So whenever there's delta x, you just kind of leave it and substitute an x if there is one. I just kind of like, I don't know how to explain the question.
Try again.
So, if there's delta x in the problem like that, you wouldn't substitute in like whatever the x value is, just leave it.
Just leave it.
Okay.
Right, because later on, we're gonna learn what to do with the delta x.
Okay.
This is when the calculus comes in. This is just algebra stuff, where we throw in some weird symbols. Instead of using x's and y's and r's and s's.
Just treat it like another
treated like another variable, right? And then we'll learn later what to do with that delta x, because it's a pain in the butt and we want to get rid of it. Are we good? Excellent. Okay. Yeah, we did that already. Okay. As we talked about the other day when somebody brought up I, imaginary numbers, I think. Did we talk about imaginary numbers? Yeah. We don't deal with imaginary numbers in here, only the real number system. Therefore, when we start looking at domains, we're only concerned about two things. Do you know what they are? Nothing. Let me rephrase the question. What's bad in the real number system? We hit on one already. Nick,
0 and denominator.
good. And the other one?
Imaginary
And how do you get an imaginary number?
like square root of negative.
Square root of a negative number. Good. No zero denominators, no negative square roots. Everything else is fair game. So the assumption we have when we start is that the domain of any function is all reals, negative infinity to infinity, unless something is going to create a problem. Then we need to find that problem. And once we find the problem, that will put our domain restriction on. Okay, so let's start with this one. Eventually, we'll talk about what that looks like. We'll use some other functions and stuff to figure out what that looks like. But what is going to cause problems in that, Black?
Where x is equal to 2, since if you square 2 and subtract 4 from it, it's going to be 0, so that's 0 in the denominator.
Good, we agree?
Yeah.
You're half correct.
Half?
Half?
Only half.
Only half, 50%, sorry. In this class, though, it's still passing.
Oh.
What do you got?
Negative
Name.
2.
Will.
Negative 2 provides the same result.
Negative 2 also works.
That's what I forgot.
I understand. So x is not equal to plus or minus 2. Anything else cause problems? Anything else make that denominator equal to 0? No. Any square roots to deal with? No. So we're good. Except, a little small thing here, this is not acceptable notation. It has to be an interval notation. Anybody want to give that a shot? Go. Open bracket here?
Yeah,
Why?
because there's not, infinity isn't like a set number, we can't. Yeah. And then to -2, and since it can't equal -2, it's also an open bracket. And then you have an open bracket.
Oh, we got the U thing in there.
Oh, okay.
Yeah.
And then from -2 to +2, open brackets again. And then final one would also be open brackets to all the way to infinity.
Well done. This is so much easier, but that's what we need to use. Sorry.
What is the use?
Union. It's a fancy math. Nobody ever uses it. People just list the parentheses and move on. But again, trying to keep the good math going here. Okay. Any problems? Review for everyone?
Yeah.
Let's talk about that function. We have two approaches to this problem. Well, there's a lot of different approaches, but two that I can think of. One is a graphical approach. One is an analytical approach. Graphical would be thinking about the graph of that function, trying to figure out where the domain is based on the picture. Analytical approach would be doing a bunch of algebra to figure out what x can and can't do. I'm optional. Which one would you prefer?
It's grass.
Graph? Okay. We'll do a graph. What's that guy look like? What mother function is it based off of, Colin?
So like that. Just trying to.
Kind of like that?
Well, I'm trying to figure that like a little loop. Not a loop, like half a loop.
Half a loop.
It's like a wave.
Okay.
Well, I know, but like,
A wing to seagull.
well, alright, it's like this.
You assume I can see that? You know, I'm old, right? You know, I can barely see your face for a while.
Alright, I'm trying to.
Just use your hand.
Yeah, that's what it was. It's like
Like this?
this. Yeah.
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 Yeah. Yeah. Where?
Top right or first quadrant.
Anywhere in the first question?
Starting from the origin. Oh, starting at 1. Well, I don't know. I'm real fast.
One, Noah? Why? Am I asking a silly question? Does everybody understand why it starts at 1, 0?
Yes.
Yeah.
Why? Yeah, we have a transformation of the mother function. So the original function that we base, the mother function that we base this off of is square root of x, which would start at the origin, as Colin said, but then the 1 moves it to the left or to the right, I forget. To the right. Okay, so this is at 1. Whoa. Ah, close enough. Colin, how'd I do?
Perfect.
That's not perfect. I mean, it's pretty good,
above,
but
we'll say above, like subpar actually. I changed my mind.
C plus?
Yes.
Okay, thanks.
Maybe a B minus if the teacher side.
Yeah, it's a big difference. Yeah, perfect. B minus maybe?
Yeah, I can do B minus.
Oh, thanks, man. Appreciate it. Helps my self-esteem. Good. All right. Do we all agree, by the way? All right, what's the domain? Oh, we've heard enough out of you today. Hey, take a break. Have a sip of water. I'm assuming that's water. Sprite?
I don't know why it's bubbly.
You should be drinking that.
Well, I was just gonna say, wouldn't you want to
It came
know?
out of the drinking fountain, so
What?
So you're just going with it.
yeah.
Just doesn't matter. If it comes out of the drinking fountain, you're good to go. Bubbly or not.
The filter was green.
Maybe the lights.
Filter was green.
And the water fountain.
Oh, yeah.
One
Name.
to infinity.
Jack.
Jack, what do you got for me?
1 to infinity.
Good. Parentheses, brackets.
The bracket and then.
Bracket.
Or wait, no.
Oh no, you said bracket. I wrote parentheses. That's my fault. Bracket 1, comma, infinity.
Parentheses.
How do you do?
Yes.
Yeah.
Perfect. Good. How about the range check?
0 to infinity.
Are you asking me or telling me?
0 to infinity.
0 to infinity.
Bracket and then in parentheses.
Well done. Now, suppose we took an analytical approach to that. You had a function that you didn't know what the picture looked like. Like in the previous example, for instance, 1 over x squared minus 4. Do you know what that picture looks like? No, so you have to come up with another method to solve it. If we go back to that other problem, we actually did an analytical approach. However, you're all smart enough to know that you did it without having to actually grind out the math. Same thing is true here. The analytical approach to this would be to look at this thing. By the way, bonus question. Does anybody know what that thing is called? Go.
Discriminant?
Nope. Discriminant would be true if you're talking about quadratic formula b squared minus 4ac. That's not a horrible answer. And your brain just grew. How's it feel?
Bigger?
Yeah, good. I wouldn't expect you to know. It's called the radicand. But anyways, from an analytical approach, what do we know about that radicand? What do we care about with x minus 1? You've already solved the problem, Bo.
It can't equal less than -1. Or, oh my god, okay. X has to be greater than 1 or greater because you can't have a negative in the square root.
Again, you solved the problem already.
Okay, then what's the question you're asking?
What do I know about, oh, here, let's do this. We'll just call that a funky shape.
Okay.
What can you tell me about the funky shape? You guys done chatting back there?
Yeah.
Good.
I'm lost, I'm sorry.
Anybody else? Go.
It's greater than or equal to 0.
Good. So that funky shape has to, what the heck? Greater than or equal to 0. As you can clearly see, this has to be greater than or equal to 0. And it can equal 0 because we can take the square root of 0. Then you go ahead and solve that, and then we get the, in this example, you get a nice pretty answer. When they get more complicated, that's going to be what happens with the analytical approach. For the square roots, if we go back to the example we had on the previous slide, x squared minus 4, most of you are able to rattle off right away what's going to cause a problem. And actually, the mathematics from that would be to set that equal to 0. Because we don't want denominators equal to 0, so we're going to solve it for 0. Wherever it solves equal to 0, that would be the problem, and we move on from there. Okay, we good? Beautiful. Let's see how far we got to go. Oh, look, there's a picture. Nice job, Colin. Mine wasn't quite as good.
It might have been better.
I had a lot of character.
Brownie points never hurt. This is not a big deal, but I did want to mention it so that I can say I mentioned it. But 1-to-1 is a function where you've got every x value has one and only one y value, and every y value has one and only one x value. Okay, like all linear functions are 1-to-1. Parabolas, for instance, would not be 1-to-1 because you have multiple x values for each y value. Okay, we good? So this is all review, right? As we get later into this section, some of the stuff theoretically is still review, but it's going to require a little bit of a jump start in your brain, but we'll get there. Okay, let's talk about some thank you cards. So we'll do this a couple times every year.